Hello. So today we're going to do some review for the midterm exam. We're going to go through some of the slides first, then we'll look at some of the written problems that we provided as samples, and then we'll come back to the slides. One thing to notice is that this says lecture 14. Normally there's a lecture 13 before the midterm, but because of just the timing and when Memorial Day fell, etc., we're moving it to near the end of the semester. So it'll be an odd numbered lecture, but we wanted to leave the slides numbered consistently with every other semester. Okay, here's the good news, which is I stress out way more about writing exams than I ever did as a student about taking them, because we want to make sure that everything runs smoothly for you. We don't want badly worded questions. We don't want incomprehensible questions. We don't want questions with 2 answers or 0 answers, etc. Well, the written problems could have multiple answers. There's always multiple ways to write one, but at least for the multiple choice, we want there to be exactly one correct answer. And we don't want it to be too hard or too easy. And the good news is we spend a lot of time preparing and getting ready for the exam. And so we want your experience to go as smoothly as possible. Now, the times tomorrow are 10:30, our normal class time starting, and then it'll end a little bit late because you've got 2 hours and 20 minutes. And then there's another time at 7 p.m., same amount of time. Our exams are normally 2 hours. We're providing the extra 20 minutes since we started COVID online exams just for downloading, uploading, my internet paused for 2 minutes issues. If something like that happens, just, if it's a minor interruption, just keep going, do what you can. If it becomes an extended problem, then post on Piazza privately, or we're going to keep a close eye on Piazza. If you can't get to Piazza, I'll try to remember to check the EECS 281 admin email periodically during the exam, but we'd really like you to use Piazza if possible. You do not have to select a time slot. Just don't take the exam twice. We will be checking. The extended time extended time for students with SSD, etc., will start at the same time. It ends an hour or 2 hours later. So the exam is going to be provided to you via Canvas. It'll be on the Canvas quiz, and all of the questions will be there. The multiple choice, it'll be question with answer, question, answer, question, answer, just like your labs. The written problems you will read on Canvas. You will download the starter files from the Autograder, and you will upload the answers to Gradescope, because Gradescope is where we can create a rubric for the grading and tell you that you got, points for doing this part of the solution correctly, etc. Don't hit submit on the quiz until you're done with both parts, because as soon as you hit submit, you lose the ability to read the written questions. So leave that until the last minute submitting on Canvas. The honor pledge, it says fill out the next day. Cross that out. I changed that. The honor pledge will be available immediately. And yes, there's no limit to how many times you can submit on Gradescope. So you can submit on Gradescope as many times as you want. By default, we will use the most recent submission. Well, really, by default, Gradescope uses the most recent submission. And there is a way in Gradescope for you to say, activate this previous solution if you'd rather do that than re-upload it. So you can do that yourself. You don't even have to contact us. Do we have slides on Canvas? These slides should be on Canvas. Let me check real quick. Canvas, files, lecture 14 midterm exam review is visible. Yes, it should be good to go. I haven't made 15 through whatever, the end, visible yet, but 14 should be visible, and I uploaded it on Sunday. Okay, So you can do the honor pledge as soon as you are done with the exam. Cross out that next day. In the past, the reason we put the starter files on the Autograder is in the past we gave a link. It was a Google Drive link that said anyone with the link can view this file, and we'd have a dozen students saying, I can't use that link. And so we know everybody who's in the class has access to the Autograder. So what I would do is make a link to the Autograder now. Oh, it looks like I'm buffering. Okay, it looks like I buffered, so I paused there for a minute. So I would make a link to the Autograder now. There's a Piazza post that has things about the midterm exam. And I should have looked up this number ahead of time. Midterm exam information is at 8:53 on Canvas. So if you just type at 8:53 into the search box, it'll bring you to that post. So you can read through that post, and we've provided most of the information in there. So like we said, we're going to have you download the starter files from the Autograder. It's got links to Autograder 1 and Autograder 2 are in there somewhere. Yeah, it's in like the third paragraph. There's links to Autograder 1 and Autograder 2. And we want to split up people a little bit. If your unique name starts with A through K, go to Autograder 1, L through Z, go to Autograder 2. And just open up those links from Piazza now and make a bookmark for them. And then open them. I would open it before the exam. Don't hit refresh at 10:30. Because if 200 people do that at once, the database server will get overloaded and no one will get to see it. So have the Autograder page loaded ahead of time. Then after you read question 25 or 26, then go hit refresh. And because people take different amounts of time to read, it won't be everybody hitting it at exactly the same time. So then also the other thing is there is no way on the Autograder to say this is visible only to the people taking it now, because we have no idea when you're going to take it. You don't have to tell us. But do not go downloading the starter files at 10:30 if you're taking it at 7 p.m. That's a send you to the honor code violation, because you are accessing exam resources before you begin the exam. So that's going to be tracked. So don't download it before your time that you take it. You don't have to tell us what time, but we will know which quiz you took on Canvas, and we will know when you downloaded the files. So during the exam, we're going to set Piazza to private posts. If you have a question, post it. Move on to another question. We'll have about half of our staff online for each exam time, hitting refresh on Piazza and answering questions as quick as we can. The bottom here that says set your browser to fill the screen, standard zoom factor, we've had people every semester who, for whatever reason, the graphics in the exam, like, hey, here's a tree, or here's a linked list, or whatever, the graphics just don't appear correctly. And it takes us a while to figure out your question, post, etc., and give you the answer. But most of those problems are fixed by making your browser fill the screen. If you're trying to make your browser fit in like a third of the screen so that 2/3 of it can be PDFs, that's when graphics start disappearing for most people. Also, one thing, when you post on Piazza, give us a question number. Don't say in the one where, because for the multiple choice, everybody gets a random selection of problems. They are selected from, basically our exam says, take 2 from this topic, the easy set. Everybody gets 2 from the easy set of questions on that topic. Take 1 from the hard set on that topic. Everybody gets 1 question from the bank of, say, 11 questions. You'll get 1 of those 11. And if there's like 2, it might give you 2 of these 20. So everybody has different questions, but we know if you say question number X, we know question number X comes from Easy Bank, this one. and give us enough text for us to identify it. You can include a screenshot if you want. You can copy and paste the text of the question, but let us know the question number and let us know something from the text of the question that we can uniquely identify to find it. We cannot view your particular questions on Canvas until you submit it. It's a lacking feature in Canvas that we cannot view your exam while you're taking it. You can use anything we have given you. And by we have given you, that does not mean we said Wikipedia so you can use Wikipedia, and we said CPP reference so you can use CPP reference. No. If you could download it from Canvas, you can use it during the exam. So PDFs, I would grab them all ahead of time just in case, download them to your local PC, have them all ready to open if you really need to. During a normal semester, you would not be allowed to have the PDFs, but you would be allowed to have a cheat sheet. That's still a great idea to have the most important things right in front of you. And if you actually write them by hand, it has two big advantages. One, research shows over and over and over again, writing things by hand improves long-term memory connections. And two, you won't have to alt-tab as much. You can just go, ooh, piece of paper, look up master theorem, blah, blah, blah. Okay, there's the master theorem. Rather than alt-tab, 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 triple-tab, find the one with the PDF, just do it by hand. It'll make it a lot easier, and you'll find that writing it by hand makes you use it less because, again, long-term memory. The multiple choice questions, there's always 24 questions for everybody, 2.5 points each. There will be 4 to 5 possible answers per question. There's no deduction if you guess and you're wrong. There's only a lack of points if you get it wrong. You either get the points or you don't. There's no penalty for guessing. So make sure you answer all 24. There is one answer per question. So make sure that you choose the best answer there. But you shouldn't have 2 that are correct. I mean, we've used this same bank of questions for several semesters, so I think we've taken care of all of the problems that were poorly worded and had 2 possible answers. The exam itself, I've already mentioned all of this. Don't submit until you're done with both parts. The display issue, we already talked about. Oh, wait, no, this is a slightly different display issue. Because there is one time limit for everybody, we had to allow the biggest amount of time. But everybody gets a fixed start and end time. So students who have normal amount of time will start at, say, 10:30 and at 12:50. When you start, it may tell you you started late because you don't have 260 minutes. Well, that's because you only have 120 minutes. If you're taking it at 10:30, you want to start at 10:30. If you start at 11:30, you still end at 12:50. Now, if something like that does happen, post on Piazza. If you tell us before it ends, we can help you. Once it ends, Canvas won't let us add 10 minutes because you started 10 minutes late for some reason. And also, don't tell us I started 10 minutes late 2 minutes before the end, because A, we may not have enough time to see it and fix it, and B, we can't verify it. Canvas to us says about 2 hours when it's about 2 hours. But when you've been, oh wait, no, actually, we don't know when you started. Don't take that back. Start on time. Start on time. We have no way of telling when you started. It only tells us how much until your time runs out. So just make sure you start on time or very close to it. Check the remaining time. This is for the SSD people. You can look at Canvas now and go to Canvas quizzes and look at your start and end time. If it's wrong for an SSD person, if we missed your form, tell us now. If you start the exam and you see in the upper right, hey, I've only got 2 hours and 20 minutes, I should have 3 hours and 20 minutes. Post on Piazza before it ends, and we can check your form, check our email, and fix it before it ends. But once you submit, we can't add time. Study materials, like we said, everything that we've gone through. The projects, we have tried to eliminate project-specific questions from the exam because there's different projects every semester. There might be things similar. There might be something involving using a stack or a queue to search, but it will be generically enough stated that you can apply what you know from a project to do it. But there is general info from the projects useful, like how to use a vector, how to use a priority queue is going to be on there. Topics, basically everything we've covered so far. Oops, I forgot to cross this one out. Strings and sequences, cross that out because we had to move that to the final. So everything we've covered so far: complexity, containers, stacked queues, priority queues, vectors, binary heaps, because that was part of the lecture on binary heaps and heap sort, not pairing heap. We've been careful to, I hope, eliminate every pairing heap question. That was just a project topic. Quicksort, merge sort, heap sort, elementary sorts, etc. Okay, so when you answer the coding questions, there is always people who have questions of what constitutes a line of code. So the answers are here in the slides. If you decide that you want to make a helper function, then just write it above the given function. If you decide that you need a structure, write it before the given function. So we'll give you a starter file, and it'll say either like you're not allowed to include anything, or here's a bunch of includes that are things we commonly use, and you can add more if you want it. So, or it might do both. It might say, here's the includes, you're not allowed to add anything else. Just read carefully in the starter file. It'll tell you what you're allowed to do for including. If you need a structure, just write it before the given function or inside the function. Some semesters, there are some problems that only are doable if you create a struct or use a pair. Our line count is based on a straightforward solution. So if we thought that a struct was the way to do this, then, oh yeah, it's going to take like an extra 2 or 3 lines to declare that struct. That's taken into account when we set the line count. We don't always write a helper function. We usually don't need it if we're doing like a top-down, and never mind, that's an end of semester topic. If a header or if a helper function is the way to do it, basically you're going to be charged 1 line for adding the header, and then of course the code inside of it. But it's not, that's still within the line count. If we say like the line count is, let's say 15, it means we were able to do it in around 10. The line counts are there because before we added them, we would have a 10-line solution and that we wrote, and we'd have people submitting 30, 40, 45 lines of code. And you're just so far away from anything that's going to work, it's just impossible to grade. So the line count is usually pretty reasonable if you're taking the right approach. Make sure, understand the problem, draw out some examples. Like, oh, I would make a vector and I would put these things in it. Well, draw it out, make that vector of size whatever, put things in it, and visualize how you would have to process it before you start coding. So how many lines of code is this? This is 2 lines of code. It's an if and the what to do if the if is true. You can write it like the top, but we'll grade it as if you wrote it at the bottom. If there's 2 lines of code in there and a closing curly brace, it's 3 lines of code. 3 lines of code. Closing curly braces never count against your total. Blank lines are not lines of code. Comments are not lines of code. So if you want to put a comment in there and take the time to do that, that's fine. I wouldn't usually do that on an exam unless I was done and there was time left over. But if you want to use blank lines to separate like this initialization from this solving the problem, from this producing the output, or whatever the solution takes, blank lines don't count against your total. So how many lines of code is this? This is 4 lines of code. If result equals, else result equals. This is a case that you could use the ternary operator. Generally, our problems usually don't need the ternary operator, and if they do, we base our line count on this version. I shouldn't say need. No problem will ever need a ternary operator. Some could be solved using a ternary operator, but if they are, we base our line count on not using it. Okay, so if you said, hey, there's an example we're going to do like after the midterm where we were counting words. So it was just something I thought of for an example. So if you add a struct, the line count here is 5 lines of code. And I also wanted to show you how, hey, you can say, I want to add a structure to a vector. You say push back, curly braces, element comma element, whatever, how many elements are in there. So it's really easy to do that. If you decide you need a structure, some semesters never need this, but some do. So we just always include this. So the line count is 5. 1, 2, 3 lines of code there, 2 lines of code there. And that's, if that's a way to do it, that's in our line count allowance. And every question will tell you what you are allowed or not allowed to use. The function header that we give you does not count. So like we'll have a line that says, return type, whatever, and if it's a question 25 templated, the what we give you never counts against your total. Includes don't count against your total because they're not code. They are grabbing code, but they are not themselves code. So it's basically what you add to what we give you, but not includes. For the ones that we provide in include files, we will either tell you you can't include anything else, you must use these, or we'll give you like the ones that we commonly use, like vector, DAC, algorithm, priority queue, utility, stuff like that. Stack, queue, DAC. We'll give you the ones we commonly use, IOStream. So if you need it, it'll be there. If you might need it, it'll be there. If you don't need it, it still might be there. Just because we've got a standard set of includes for the midterm, we got a standard set of includes for the final. So if you're allowed to use anything, we'll just give you a list of them that are used in the first half of the semester, and it'll tell you whether you can add extra includes or not. For integer types, use whatever makes sense. If your code does not compile on Gradescope, we will still grade it by hand. We did this before we submitted files to Gradescope. When we gave actual in-person exams, we would scan the exams and we would grade the scanned code on Gradescope by looking at it. So if your code doesn't compile, but you're sure it's really close to right, but you can't get that integer typecast to work, leave it, move on. We will grade it. So you're much more likely to get points if you have like an invalid integer or a missing semicolon and go on and get the other problem solved than if you spend a half an hour trying to get it to compile and don't even start the second one. You're much more likely to get more points if you have 2 that don't compile but are really close to right than 1 that compiles and 1 that is empty. So if you stick to what we give you, like if we give you a vector of ints, well, then make a vector of ints and treat them as integers. If you treat things consistently, it'll be fine. We try not to set the Autograder to be pedantic about the compilation step and integers. So we try to be less pedantic than the Autograder for projects and labs is. You are just going to, for the written questions, you are just going to download a CPP file and upload it. Make sure the name matches. I see people all the time who they download the starter file, then they download it again, then they edit the second copy, and we get a name like question_25 parentheses 1.cpp, and the Gradescope can't compile it because it's the wrong file name. So just make sure when you submit it, it has the same name that the question spec says. So they'll actually be named question_25.cpp, question_26.cpp will be the, actually question_25.h and question26.cpp. So make sure you've got the file names the same as what you downloaded. Okay, now I'm going to switch over to the exam and my thing that lets me look at PDFs and edit them, doesn't like it when I change to it. So I got to reopen this document. Okay, go to page, looks like that one. Okay, try to get this to look right for you. Okay, so this is the practice exam that we gave you. This is a real exam from a previous semester. And I don't know where Professor Darden is. Ojun, that would be one line. Oh, my Apple Pencil battery is low. Oh, didn't think of that. Okay, I'm going to plug in my pencil, and I'll talk for a minute while my pencil charges. Happily, it doesn't take too long to charge the pencil. Okay, so this is a real exam from the past, and we gave you the format of the question. And we've got some examples, or one example here. And so let's talk about this question. So it says, I'm trying to view where's my PDF preview? My iPad, there we go. Trying to make sure it looks right on yours. Okay, so we've got the template for the function. Sorry about the gray word practice here. We did that because in real semesters, people send the PDF to like a printer in the Duderstat. And if it sits there for too long, someone from the Dude will come along, and then we get an email that would say, your midterm exam has leaked. And I read the title of the email and my heart stops. I'm like, oh my God, no, how did this happen? And then I look at the PDF and I'm like, oh, that's the practice exam. And they didn't notice that it said practice up at the top, that one little word. So that's why I put the big gray watermark across it, is to stop having heart attacks when printouts got left in a printer and someone noticed. So that's why the big gray thing is there. So we've got the template header. We've got what it's supposed to do. It says, okay, so this one is supposed to copy elements from the range first last to a range beginning with result, except that in a consecutive group of duplicate elements, only the first one is copied. The return value is the end of the range to which elements are copied. And this is end in an STL sense, inclusive, exclusive. So really, the iterator return should be just past the last value written. Okay, it says complexity linear for elements in the ranges, exactly last minus first, applications of operator equals, and at most last minus first assignments. The complexity for the STL question, we got to understand STL questions. The goal here is to write it like the STL would. The goal is to do things with iterators that are valid with iterators, do things with data that are valid with data. So when it talks about how many times you're allowed to do something, that's talking about data. The complexity is always talking about the size of the data and what you're allowed to do with data. In addition to the equality tests on the data, you're going to have tests on the iterators to make sure you're not off the end. But the complexity is always stated in terms of what we're doing with the data. Okay, so we're allowed last minus first applications of operator equals, meaning we're allowed to test, is this data item equal to that data item? And we're allowed to do, at most, last minus first assignments. That would be writing stuff to the output. So here's an example. So it says, example, if you execute this code. Okay, so we've got integer array data has 6 elements, and there's the elements 133, 110, and output is of size 6. And it says, call unique copy, give it data and data plus 6. Well, data and data plus 6 would be inclusive, whoops, I'm in the wrong part, inclusive, exclusive iterators. Those describe where the input is. The output, it says, hey, this is the inclusive start of where you should write output. Okay, so then it says, you should produce this in array output. So when we're done, we should have 1, 3, 1, 0. So the sequence of multiple 3s, only one of them ended in the output. The sequence of multiple 1s, only one of them ended in the output. Now, before we write the code for this, let's talk about what we're allowed to do. So we are allowed to copy construct iterators. So in fact, that's done in the header of the function. The iterators were copy constructed when they were given to us. So iterators can always be copy constructed. All iterators can be plus plussed. All iterators can be dereferenced. Now, and beyond that, it depends on the type of iterator. So input and forward iterators can be read from. Input iterators you can read once, and then you must plus plus. Read once, plus plus, read once, plus plus. That's an input iterator. A forward iterator, you're allowed to read multiple times before you plus plus. So when you dereference an input iterator or a forward iterator, you're allowed to look at it. Input iterators you can look at once before you plus plus. Forward iterators you can look at once, twice, 3 times before you plus plus it. Output iterators, forward and input iterators. You are also allowed to compare forward and input iterators to another iterator of the same type. Okay, output iterators. Output iterators can be written to, they cannot be read from. Output iterators must be plus plussed after they are written. You cannot write twice and then plus plus. You must write plus plus, write plus plus. They cannot be compared. There's nothing to compare them to. I've got one output iterator. What am I going to compare it to? Itself? You're not allowed to compare output iterators. So that's our rules. So then what we've got to do is solve this particular problem. Now every one of these problems is slightly unique. Some will need a test at the beginning to see if the input range is empty, some don't. Some will just go straight to a while loop, and hey, if the input range is empty, the while loop is done. So this one is one that needs a test up front. And let's think about why. Let's think about how we do this. Okay, so I've got 1, 3, 3, 1, 1, 0. So I've got to see if things that are adjacent are the same. So really, I'm going to need multiple input iterators or forward iterators. I'm going to have multiple forward iterators into first last, because I'm going to have to be able to look at, dereference this one and dereference that one and check if they are the same value adjacent to each other, if they're sequential values that are the same. I need 2 iterators because you are not allowed to say things like this. You're not allowed to say like if dereference first equals dereference of first plus 1. You cannot do that. Why not? Because this is pointer arithmetic. Pointer arithmetic is only valid with random iterators. So we can't do that. The statement of the problem says the complexity is last minus first. Am I allowed to write a line of code that says like n equals last minus first? No, you can't write code like that. That's only allowed for random iterators. So don't do it. You don't need to do it. This is a statement of the complexity. It's basically telling you that n is equal to the size of the range last minus first, but it doesn't mean you can write code that says last minus first. Okay, so that's why I'm going to need 2 iterators, because they are not random iterators, they're forward iterators. So I'm allowed to have like 2 iterators because I'm allowed to copy construct them. I can make a copy and either keep the original one here and move the copy forward, or leave the copy here and move the original one forward. Doesn't matter. I'm going to have them one apart. For me to have 2 iterators that are one apart, I would have to have an input range of at least 1. Because you could say, well, what about at least 2? Well, if I get 1 and I move forward, I'll be off the end and I'll know that and I'll stop. Okay, but I'm also, here's another thing. If we think about the input, the very first value has to be in the output. Because even if there's a duplicate following it, the easiest thing to write is the first value I see. Like when I see 10 3s in a row, it's easy to get the first 3 to the output and then skip the other 9 than it is to skip I don't know how many and make sure I get the last one. So because we're going to need 2 iterators that are one apart, and you're not allowed to increment and end iterator. And because we're going to have to copy the very first element of the input to the output, then we're going to have a test. So I'm going to check here if first, F-I-R-S-T, if first is equal to last, then I can return. Well, wait a minute. I can't just say return semicolon. I got to return something. I've got to return an output iterator. Well, the only output iterator I've got is result. And is result just past the last thing written? Well, yeah, I didn't write anything, so I'm telling them the output is empty. Okay, so I return result. So that's basically saying the result is empty. Okay, now that's done. Now what I want to do is I want to get the first thing in the input over to the output. Okay, so I've got to say dereference result plus plus. I'm always going to plus plus when I write to result. I'm going to set that equal to dereference first. And I don't want to move first forward because remember, I've got to have two iterators that are pointing to adjacent elements. And if I plus plus first right now, then I won't be able to go backwards to the previous element. Forward iterators, they're only allowed to be plus plus. Output iterators can only be plus plus. Same for input iterators. These are not bidirectional, so they cannot be minus minus. So I'm just going to set it equal to dereference first, and then I'm going to need a new iterator. I'm going to need, like I said, I'm going to need two adjacent ones. I can think of them as like the current and the next, or the previous and the current. I'm going to think of it as the previous one and first, what was given to me as first, I'm going to think of as the current one. I'm going to have an iterator for the previous one. So I need a variable of type forward iterator, but I don't like writing down or even typing a forward iterator. That takes too long. This is a great place for auto. Auto previous is equal to first, and then I'm going to plus plus first. So what I'm going to have basically is now previous points to the 1 in the input, first points to the first 3 in the input, and then there's another 3 and a 1 and a 1 and a 0. So that's where I am right now. Previous points to 1, first points to 3, and now I'm ready to start my loop. So now we've got to loop through as long as I'm, let's say it in English first, as long as I'm not at the end. If I'm looking at different values, I should send one of them to the output. And I've got to make sure that iterators move forward and stuff like that. But just a general idea is I'm going to look at 2. If they're different, one of them is going to have to go to the output, and then I'm going to move forward. I'm going to have to move everybody forward. Okay, so there's my English. So as long as I'm not at the end, while somebody is not equal to last. Could we write less than here? No, because we don't know whether the iterator less than makes sense. If I gave you linked list iterators, less than is an invalid comparison for linked list iterators. But iterators can always be tested for equality and inequality. So we always want to use like equals equals or not equals on iterators. So up above we did equality. If I'm at the end, I'm done. Here I want to say while I'm not at the end. So while somebody is not equal to last, my loop's going to keep running. Okay, now looking at my diagram over on the right, who do I want to stop? Do I want to stop when previous is equal to last, or do I want to stop when first is equal to last? If I keep going until previous is equal to last, that would mean that at some point previous was before last and first was last, and I'd be trying to look at an element that exists and an element that doesn't exist. So this has got to be first, because I've got to look at adjacent things. If one of them is off the end, I can't look at adjacent things. So of the two things, the two iterators that are moving forward, the one that is the furthest forward or the closest to last is the one that we compare to last. Okay, so while I'm not off the end, I've got to do a check to say, hey, am I looking at different elements? Because if they are different, I want one of them to go to the output. So I need inside here, I need an if statement. If, and I'm going to have to do some dereferencing. There's a problem though. Statement of the problem says I'm only allowed to use equality test on data. Why? Because the STL doesn't like to force data to overload too many operators. So basically, if your data type supports less than and equal, you can do anything in the STL using that data type. So the STL doesn't demand that you implement not equal to. So it says in the statement of the problem, basically when you do data tests, you've got to compare for equality. Well, I could say if they're equal, do nothing, else do something, but that requires an extra line for the else. So what I'm going to do instead is I'm going to say if not test for equality. Okay, so if not dereference previous equals dereference first, parenthesis. Okay, so if those things, or if those iterators point to different values, then somebody has to move to the output. And result has to get incremented. So dereference result plus plus equals dereference of somebody. Okay, well, let's look at where we are, and let's look at our output. Output right now has in it, I started to draw a line there. Output in it right now has a 1, and result points to here, because remember before the loop started, we got the first value to the output and result moved forward. Okay, so do I want to write previous to the output or do I want to write first? If I write previous to the output, I'm going to get another copy of 1, and that's wrong. So it's got to be dereference first. If you draw this out, it's easier to get the code right. Now, we haven't yet moved first. There's a couple ways we could do this. I'm going to put a semicolon here. We could also do equals dereference first plus plus semicolon. Okay, in the next line, I'm going to say, my solution said previous is equal to first plus plus. We could instead do this as plus plus previous semicolon. So we would have to be consistent. We would either have to do these like in the box or those that are in the code. But either way, both of them have to move forward. So I did this line of code like I did that line of code. That's why I thought of it that way. Previous gets set equal to first gets incremented, everybody moves forward. But the other way on the right is equivalent also. Okay, well that's the end of my while loop. You do not have to comment your closing curly braces. I always do, because I'm a professor. I want to make sure it's clear where my loops begin and end. If you were writing this by hand, I would recommend the comment, just because when people write it by hand, their code tends to wiggle back and forth, and it's almost impossible to read sometimes without the comments. Okay, then after the while loop's done, we got to remember to return result, semicolon, and then curly brace. And in the starter files, this curly brace and a comment, question 25, or whatever, will be given to you. So in the starter file, that'll be there. That closing curly brace and the comment will be there for you to know, hey, this closing curly brace is the one that goes with the function, or unique copy, or whatever it's called. All right, so there's a solution to that. And I haven't been keeping an eye on the chat window. Hopefully it's not too crowded. Okay, yep, Professor Jordan's keeping an eye on it now. So that's my solution. Also, I mentioned this in the Piazza post 853. When lecture is done, I've got it set for 12:01. a PDF with all of these answers will appear on Canvas. It's all scheduled. So it'll have the multiple choice, it'll have the answers, it'll have an explanation for every multiple choice will be in that answers PDF. The code will be there written out. It won't have all the explanation for the code, but it'll have working code. Okay, so that one's done. Let's move on to the next question. Okay, blank page. This was, like I said, a real exam once. Okay, finding max elements. Okay, so we got to read the question here, understand what we're doing before we move on. Okay, so what it says is, suppose we're given an array of integers, size n, so that was given to us, and we can look down below and see the function header has those things. Okay, so we're given an array of integers, a size n, and a number k. Okay, I want to return the k largest elements. Oh, looks like I'm missing a period there at some point. Period. Output does not need to be sorted. You can assume that k is less than n. Okay, so I don't care what order the output is in. It's just got to have the k largest. So this one we thought was pretty straightforward. We didn't give an example. But, okay, let's just run through a little example before we start. All right, let's do it up at the top here. Okay, so if I had my, what's called my integers is called array. Okay, so I've got ARR. Okay, so I've got ARR, and it's got values in it. And so let's say ARR was 5, 1, 5, 3, 2, 6, 8, 10, 0. Okay, and then so they would give you the size would be n would be equal to, now I got to count these 1, 2, 3, 4, 5, 6, 7, 8, 9, n would be equal to 9, and let's say I said I want k equal to 4. I want the 4 largest. Okay, when I'm all done, I should be returning a vector containing, in some order, I don't care what order, a 5, a 6, an 8, and a 10. In any order, doesn't matter. The fact that there's two, if k was 5, then there would be 2 5s in there. If k is 4, there's 1 5 in there. So we don't care about duplicates or anything like that. Just get the largest ones, put them in there. Requirements. Your solution must be faster than O of n log n time. You may use up to O of n auxiliary space. So, what that tells us, the solution must be faster than O of n log n, tells me I cannot just sort this and grab the big end. That's out. If you go over the requirements, so there were requirements on the previous problem, there's requirements on this problem. If you go over the requirements, there will be penalties to points, and it will be more significant penalties the more egregious your abuse of the requirements is. So, for example, people who did this and just did sort and then copied the elements got a big deduction. People that tried to do something clever and happened to go over accidentally, like their loop variable is wrong, but their approach was right, but their loop variable was wrong, lost less points than people who just went, hey, I'm going to sort it just because I know I'll get the solution even though it's over. Lost a lot more points than people whose loop condition, if they had just changed the loop variable, would have been fine. And it really comes down to, did you even try to meet the requirements here? Okay, so it says it must be faster than O of n log n. I can use up to n auxiliary space. So the may use up to O of n auxiliary space makes me think, well, okay, maybe I should be using up to O of n auxiliary space. Maybe it's needed. Okay. Well, then what could we use to get the largest elements and be faster than O of n log n? Well, we could, if we can't sort the darn thing, then we could use maybe a priority queue. Now, if I use a priority queue, I've got to be careful, because if I create a priority queue and then I say, hey, let's push these one at a time, that's n log n. It's not quite as bad as sorting because you might do good things after that, but it's a bad start. So creating a priority queue is a good thing to do, but pushing them one at a time is a bad idea. And just like the priority queues that we implemented for Project 2, like sorted binary pairing, the standard priority underscore queue has a range-based constructor. Just like data vector, right? If you looked at what unordered PQ did, it said, hey, when I need to initialize from a range, do the base class constructor, comma, data, curly braces, start end, because data vectors have an constructor that accepts 2 iterators. Well, so does priority underscore queue. So we need to throw stuff into the priority queue using the range-based constructor. So we have to do that. We can't push one at a time. Now, there's a couple ways we could do this. We could throw everything into the priority queue, and then we could pop off the k largest. We wouldn't pop off all of them. If we pop off all of them, that would be n log n. But if we throw them in with the range-based constructor, how long does it take to create a priority underscore queue? Well, it's O of n, because it's a binary heap underneath the hood. The STL's priority underscore queue is behind the scenes a lot like our binary PQ. It's a binary heap stored in a vector. So we create the priority queue with the range-based constructor as O of n, and then we could pop them off. The highest priority k could get popped off one at a time. But we're only going to do that k times. So instead of n log n, we would have O of n to construct it plus O of k log n to pop out the k largest. And it says you can assume that k is less than n. So that's critical. Because k is less than n, we can run a loop k times, popping things out that is a log n operation. So that's one approach. Throw everything in, pop off the k largest. And that would have to be a max priority queue. Biggest values are on top because the biggest values are the ones I want in the output. Another approach would be, hey, let's put k of them in there. Let's keep the largest ones. So I'm going to put k in there, and then the rest of the time from index k to the end, I'm going to push one and I'm going to pop out the smallest. So that way my priority queue always contains the largest I've seen so far. So if, like, say k was 4 here, I would put 4 of them in, then I would push a fifth and pop the smallest. Then I would push another, pop the smallest, push another, pop the smallest. And then when I'm done, whatever's left in there would go to the output. That would be n log k, right? It was O of k to construct it, the first k, then n minus k times, I did a log of k operation. One goes in, one goes out. And then when I'm done, I did another k log k operations to pop them out. So it'd basically be O of n plus n times log of k, because I keep the priority queue at a size of k, but it's got to be a minimum priority queue where minimum value is the highest priority, because I want to have the first 4, one more, pop the smallest. I'd have the 4 largest I've seen so far. So both solutions are in the slides, or in the answer document. So both solutions are in there. We're going to write one of them together now. So let's write the max priority queue is the easier one to write, I think, because you don't have to say priority queue event, comma, vector event, comma, standard, blah, 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 to override the comparison functor. Okay, so I'm going to need a priority underscore queue. It's going to be a priority queue of ints because that's what I was given, was an array of integers. And let's just give it a name. Let's just call it PQ. Okay, so we get a name PQ, and then we need the range-based constructor, which would be ARR, comma, ARR plus N. So this is basically saying ARR, comma, ARR plus N is my inclusive, exclusive iterators. So that throws them all into the PQ. That's O of n time. Now I'm going to need a vector for the output. So I could call it like vector of, going to be ints again, because this is what I want to produce. I got to return a vector of ints. Vector of ints, we could call this output result. I forget what I called it in the slides. Let's just call this result. Semicolon. What I don't want to do is I don't want to make it size k. I don't want to pre-size it or resize it. I'm going to want to do pushbacks. So I don't want to resize it or pre-size it. I don't want to put, like, if I put k in parentheses and then I push back, I would have k zeros followed by the k largest. And that would lose me a few points. Not a lot, but it would lose me a few points. So we don't want to say this one is size k. I could, optionally, I could say like result dot reserve, whoops, I can't type. I could say reserve of k. That one's optional. You don't have to do that, but I always do that. I always reserve if I think I might. Okay, so I've got my priority queue set up. I've got my output set up. Now I need a for loop. Okay, so I need a for loop for, let's see. So I need a loop variable, and I'm going to be comparing it to n or k or something like that. So this better be a size t also. Doesn't have to be, but it's the easiest thing to do. Size t, I is equal to 0. I is less than, okay, so I've got everything's in there. I need to take the k largest off, so this has got to be I less than k plus I. And I'm not sure. I think I'm going to need one line of code in there. Yeah. Okay. All right. So I've got my loop. Now what I've got to do is I've got to take the top of the priority queue and put it into the vector. So that would be result dot pushback. What am I going to push back? PQ dot top. And then I immediately have to PQ dot pop. Here's a suggestion, and I've seen people do this in the project. Always write top and pop following each other. Don't do a top, do 10 lines of code, and then a pop, because it's easy to forget the pop. And if you do that, you've got an infinite loop, or you've got wrong results or something. It's easier if you always write top and pop one line of code apart. It's easy to see, it's easy to verify that it's done, it's harder to get it wrong. So when I write code, I always do my top and pop on adjacent lines so that I don't forget. Okay, so that's the end of my for loop. So that's got everything I need into result. That's the k largest. The priority queue is still hanging around with n minus k values in it. That's fine. I'm just going to return result. And that's the end of my function. So this one's actually, it's find k max. Okay, so that's the one approach of fill the priority queue with everything, pop off the k largest. The opposite approach of create a min PQ, put the first k in there, etc. That one's in the solution PDF also. It might, I can't remember, it might slide onto a different page, but it's in there. It might slide onto a separate page, I forget. There are shorter ways to do this. There's things like nth element, there's partial sort, and this thing it says 15 lines of code. So let's count our lines of code here that it took to do this. So we got 1, 2, 3, 4, 5, 6, 7. 7 lines of code. and we had a limit of 15. I think the other solution, the K largest, or sorry, the K smallest, I think the K smallest was like around 10 lines of code, and then we added about 50% buffer. So generally, the amount of code you're allowed is approximately a 50% buffer. So like if it says 20, we probably did it in about 12 or 13-ish, or about 13 or 14. If it's, like 10 lines of code, it means we did it in about 6. So if you're looking at significantly over that, you probably are on the wrong track. If you're close, you can lose basically 1 point per line of code over the limit. And if it works, that might be better than, trying to restart and not finishing. But if you're a little bit over, it probably means you've done something inefficiently, like, you looped when you should have just used a range-based constructor or something like that. In this one, we have to use the range-based constructor to meet the target complexity goal. Okay, so that's the 2 written problems that we gave you on the practice midterm combined. Like I said, the answers will be revealed at like 12:01. I think I got it set for. Okay, now let's go back to the slides, and we got a bunch more stuff in here. Okay, let me see my preview if that looks good. Yep. Okay, so we're back to the preview of the slides. Okay, so we've got things that are on the exam. So complexity analysis. Gave an example here of this is the one something we've already looked at in the upper left. Hey, it sounds like binary search better come out to be n log n when we do the analysis. The bottom one is the slightly inefficient version of the produce the product of every element except for the current one, but it doesn't have bugs when there's zeros in the input array. So those should come out to log n and n squared. Here's merge sort. It says write the recurrence relationship. So some problems on the exam, we might ask you, here's some code, what's the recurrence relationship? Or we might ask you, here's some code, what's the complexity? So this one says, what's the complexity of this? So we're going to do this one, we're going to have to do both. We're going to have to write the recurrence relationship and solve it. So we've got some code here. So I've got to have a recurrence relationship T of n is equal to, I've got a base case. Don't worry about the base case, that always exists. I've got a recursive call and a recursive call to T of n over 2 plus merge them together when we're done is O of n. And we've got something we can throw into the master theorem. A is equal to 2, B is equal to 2, C is equal to 1 because that's the exponent of this polynomial portion. So that's C. So then we've got A is equal to B to the C power. And so that tells us we're in case 2. And that tells us we should have a complexity of big theta of n log n. T is standard for time. Okay, so then there's the equation. We plug it into the master theorem, and we can write down the base case also. So I've got the whole master theorem here in the hidden slide. So we've got it. We figure out we've got A and B are equal to 2, C is equal to 1, A is there. We look that up. That's n to the C, so that's n to the first, log base 2 of n. So we've got big theta of n log n. Now we've got some questions here that are not the best exam question, but made to make you think. So it says, what's the best container if it will be used primarily to locate objects within it using binary search? And our choices, our options are singly linked list, doubly linked list, and vector. And think about which and why. So, okay, what's the best for this? What's the best if new objects will often be added immediately before specific existing objects? And what is the best container if you must store a small number of very large objects? Okay, memory is scarce, and the most important consideration is to store as many of these objects as possible in the available space. All right, so let's move on to the answers for these. So let's say, or we can just do it together. So what's the best one if it's going to locate objects using binary search? Well, no type of linked list allows skipping to the middle in O of one time, so we'd want to use a vector for this. If it was a choice, dec would also be good, array would be fine, linked list is bad for binary search. Okay, what about if, what's the best container? If new objects will be added immediately before existing objects. So if we're going to be adding before existing objects, we know that the vector is going to be somewhat inefficient. Because if we do that with a vector, we have to move everyone over to make room. So we're going to go with one of the linked lists. Well, now it comes down to like singly or doubly. If I'm trying to insert before this one, so I've got I've got a pointer that points to this one. If I want to insert before it, then I have no easy way to go backward in a singly linked list. So we'd want a doubly linked list where I could say, hey, let's go backward one. You get a new next node. This one gets a new previous node. There we go. But to add it before this one with a singly linked list, I don't have an easy way to do that. Okay, what's the best container if I have to store a small number of very large objects? Now, if this one is slightly ambiguous, if we didn't know the number up front, we would want to go with the singly linked list because nodes only exist when they need to. We add things one at a time, new nodes get created every time we add something, singly linked list would be great. If we knew the size up front, then vector would be fine. But if we just know we're going to be given a number that will fit in memory, but not if we're wasteful, we don't want to use a vector. Because I don't want to let it grow by doubling, like double from go from 0 to 1, 1 to 2, 2 to 4, and only have 3 things. I don't want to resize it by one at a time, having to copy that huge chunk of data. So I would go with a linked list here if I don't know the size up front. If I know the exact number up front, we could do a vector resize or a vector reserve. But if we don't know it up front, singly linked list. Okay, there's the answer slide. What about if we want to know the worst? Okay, so I've got to know what's the worst container if we're going to store a large number of 1-byte items, like chars, and memory is scarce. Or just we know n is going to be large. So I know n is going to be large and I want to store lots of chars. Well, then a worst one, think about a doubly linked list. For every char, I've got an 8-byte pointer to the previous and an 8-byte pointer to the next. I've got 1/17 of my array is data and the rest is pointers. That's like on the order of 4%, 1/17. 1/17 would be 6%. So I'd be a little less than 6% of it is data, a little over 94% is pointers. Okay, that would be terrible. All right, what is the worst container if I'm going to frequently insert new items anywhere? Well, inserting new items anywhere is bad with a vector because anywhere could be the middle, anywhere could be the beginning. Vector would be bad for that. Dec would be decent. The closer you are to either end, the better the dec is. Linked list would probably be the best if I'm going to insert items anywhere. Okay, what is the worst if I'm going to insert new items at the beginning? Oh, totally vector. Worst at the beginning is vector. Linked list is great, doubly linked list, great. A dec would be great, pushing at the front would be fine, but vector's terrible at this. Okay, hopefully I got all those right. Yep, okay. So next slide. So we want to say stacks and queues. We got a question here, which, let me see how we're doing on time. Okay, I'm going to give you a few minutes to think about this one before we look at the answer, and we can actually write out the answer on this slide. So it says, implement a queue using 2 stacks. Given the class below, write the pop function. So what we could do is I could just say, hey, I'm just going to write it right here. Just going to get rid of that semicolon. I'm going to put an opening curly brace over there, and oops, that's supposed to be an opening curly brace, and then I'll write the code like right here. Okay, so we could write the pop function. Actually, let's move it up just a little bit. So here's the opening curly brace, and here's where we can write the code. So take a few minutes, take 2-3 minutes, think about this, and I'm going to get a drink of water, and we'll come back and talk about it. So one thing to think about here is what happens if we do a pop, what happens if it's followed by a push, etc. So you can see from the declaration, push puts things in S1. So pop is going to have to do things differently. It's going to have to make use of S2. Now let's do a little example. Let's say I push 1, 2, and 3. Okay, so then S1 would have 1, 2, 3 in stack-like order. If someone says pop, I want to get rid of the 1. So let's put things into S2. Let's move them over here. 3 goes to S2, get rid of it. 2 goes to S2, get rid of it. Simplest way to write the code is 1 goes over to S2, we get rid of it there, and then we get rid of it here. Otherwise, I'd have to have a weird looping condition, etc. So, and it would be weird if there was only one of them. I might get it wrong. I might have a seg fault. So it's easiest just throw everything over to S2 and then just pop from S2. Now the real question is, can I stop there? Can I just leave everything in S2? Well, then what would happen if someone pushed? Well, then they push a 4. So then I do a pop, and then I push 4. Okay, so 4 goes over here. 4 is now at the top of S1. If someone says pop, I can say, okay, well, what I really want to get rid of is the 2, and it's in the right place. It's in S2. We'll just get rid of it. Fine. Someone says, I want to look at the front of your queue. Oh, well, it's 2. It's the thing in the top of S2. So I think it's more efficient and less code if we just leave them over there in S2. Okay, so what we've got to do is we're going to need to do extra work if S2 is empty. If S2 is empty, we got to move everything over to S2. So if S2 is empty, then I've got to move everything over. So now I need a while loop. While S1 has things. So while not S1.empty. You could write this differently. You could say while S1.size is greater than 0, if you think of it that way. I think of it as not empty. You could do it while size is greater than 0. Either way works. They're both equally efficient. Nothing to worry about there. Okay, so while that's true, I'm going to do an S2 push of S1 top. It's a stack. Okay, so I'm going to push the top of S1 over to S2, and then I'm going to get rid of it from S1. So that's the end of my while loop. That's the end of my if statement. And then what I can do is I can just say, hey, now I can do the S2 pop. And then that's the end of my function. Okay, so let's see. I think I'm pretty sure I got that one right. Okay, so if it's empty, we got to move things over, get rid of S2 when we're done, we leave it there. What about the front function? So what if we had a function we had to implement front? It would basically look the same as this, except we would have to change this line to say return S2 dot top. So it works the same way. If S2 is empty, we gotta move everything from S1 over to S2, and then we show them the top of S2. And if they put more things in S1, fine, we'll keep showing them the top of S2. And if they pop, we'll pop it from S2. But when S2 becomes empty, then we move everything over again. So that would be how we do front. Okay, want to get through the next couple slides. We don't have a lot left, but I want to make sure they get in the video. I don't want to go over by too much. Okay, so sorting. It says, unless otherwise stated, what's the best, just in general. So unless otherwise stated, use the best, most adaptive version of a sort. That's general advice for the whole exam. If we don't say otherwise, assume we want the adaptive bubble sort, adaptive insertion sort. Selection sort is adaptive, but so slight that it's not a big deal, so it shouldn't matter either way. But for bubble and insertion, we want to use the best one, the most adaptive. Okay, so that's in general. Okay, so then it says, which sort is best in these circumstances? And these are vague questions. Array that is almost already sorted. So we know if it's almost already sorted, then insertion sort always works great. Bubble sort works great if it's bubbling in the right direction. Like if I bubble small values to the beginning and I have one big value at the beginning, bubble sort's not that great because it'll make one pass, do a swap, make another pass, do one swap, make another pass, do a swap, make another pass, do a swap. It'll do one swap on every pass. But if it has a small value at the end, it'll bubble it towards the beginning, and vice versa. So if bubble sort is bubbling in the direction that the out of order elements have to move, bubble's fine. But insertion is always good if there's a few things out of order. Okay, next one says very small. Okay, well, whatever very small is, we know insertion sort is the best on those. Even though it's n squared, when n is small enough, like 16 to 32, nobody beats insertion sort. The more complex sorts don't have time to ramp up to their cool n log n complexity because insertion sort just makes great use of the cache. The adaptive version has very tight loops. It's really, really great on small data. Okay, then let's move to the other end, the very large. Okay, so very large tape drive, meaning it does not fit in main memory. If it doesn't fit in main memory, we've got to do merge sort for this one. So that's what merge sort was made for, was things that don't fit in memory. Okay, let's do the large. So large, it says it's about as big as main memory. Now, if it's about as big as main memory, I cannot do a merge sort because I would need O of n memory to do the merging step. So merge sort is out. Quick sort could be good, but remember, quick sort is going to use log n memory. If memory is so tight that I'm almost out of heaps, the heap is almost exhausted, and the stack grows towards the heap. And if the heap is allowed to use up part of the stack space if needed. Basically, if they hit each other, we die. So I would probably avoid quicksort here because it does use that stack space for log n calls. And if that log n is going to fill up memory or overfill memory, then I might skip that and go straight to heap sort because heap sort is in place. Heap sort is guaranteed to be n log n. Sounds good. Medium, when it says medium is kind of vague. That's the really vague part of this one. Medium, I would say quicksort is probably the way to go, quicksort. Unless quicksort does a terrible job of partitioning, then quicksort usually does a pretty good job in general. Unless it partitions badly every time, it does a pretty good job. And it's unlikely to partition badly every time unless someone created data maliciously. Okay. Oh, whoops, I forgot one. I forgot a question apparently. It said, oh, you're using quicksort on a very large input and it's taking longer than I would expect. What happened? Well, what happened is the partitioning is going badly. Like every time the partitioning is going badly and I'm progressing towards n squared. So this is why intro sort was developed, is that if quicksort starts doing a bad job over and over and you notice it, bail out and use heap sort to finish this region that quicksort keeps doing terrible choices. Okay, binary heap question. So it says, draw the underlying array for this heap. Okay, that's not too bad. 81, 18, 14, 9, 7, 1, 5, 2, 4. I just go top to bottom, left to right. Okay, push the value 47 and use fix up. Okay, well, if I'm going to push the value 47, easiest way to do it is to draw it in the heap and then make the corresponding array when it's done. So I would say, okay, so if I'm going to push 47, so 47 has to go left of 7. I'm kind of cramped for space. So left of 7 is 47, and then I have to use fix up. So 47 swaps with 7, 47 swaps with 18, 47 does not swap with 81, so then when I'm done, my underlying array would be 81, 47, 14, 9, 18, 1, 5, 2, 4, and 7. So there's my array after I'm done. Okay, push 7. Oh, whoops, apparently I prepared the slide for it, but I did it by hand. Oh well, if I'd known that, I would have moved forward. I forgot I did it by hand on there. Okay, priority queues. So it wants to know what's the complexity of each of these. All right, so we've got unordered, ordered, the sorted array, and the binary heap. Okay, so to create a range, unordered, let's do unordered everything. Unordered, create a range is fast, it's O of 1. Or no, creating a range would be n because we got to copy everything in there. Okay, so it's O of n to copy them, but we don't have to do anything else. So we got to copy them, and then we're done. Pushing is O of 1, we just throw it on the end of the vector. Top would be O of n, I've got to go find it. I've got to go find the maximum element in the array. And then pop would be either O of n for unordered PQ or O of 1 for unordered fast PQ. So that basically, that assumes that top is followed by pop. If top gets followed by pop, top remembers the index of the most extreme element. Pop says, hey, if that index looks valid, I'm done. I can get rid of it. How do I get rid of it in O of 1 time, though? I say, hey, this is the one I want to get rid of. Let's replace it with the back of the vector and then pop back. The vector really is unordered because things just change their relative position. Okay, sorted. The range-based constructor would be n log n. N to copy it, n log n to sort it. Total cost is n log n. Push is O of n. Once I find the right spot, people have to move over to make room for it, is O of n. Top is easy, it's at the back. Pop is easy, it's at the back. O of 1 for each of those. Okay, binary heap gives us O of n to create the range, the heapify operation. The heapify, remember, is the bottom up fix down is O of n. Then push is log n. We push to the back of the underlying vector and fix up. Top is O of 1. We know it's at index 0 or index 1, depending on our base. And then pop is log n. We replace the root with the last, pop back, and fix down. So there's the comparison table. So this, because everything will eventually be pushed and popped, if we look at the sum of these lines, it's n, n, and log n. That's why the binary heap is a winner. Okay, strings and sequences, we can stop here because remember, we didn't get to this. I forgot that slide was in the review. So we can just cross that slide out. And so we're all done. We're a few minutes late, we're all done. We'll see you in Professors if you've got questions, and we'll see you tomorrow for the exam. Good luck, everyone.